Today we are going to have a look at integration using U-Substitution. And we can start by solving our first example. And to apply U-Substitution, you need to define two parts, which is U and du. And whatever U is, du will be the derivative of U. If we let U to be cos theta, then it's not going to get rid of sine squared theta plus 1. So we can let U equal to sine theta. And then we can see that the differential of U with respect to theta is equal to cos theta. And from this equation, we can make d theta the subject of the formula. Now that we have d theta and U, we can substitute it into our original equation. Our equation then becomes the antiderivative of u squared plus 1 in brackets multiplied by cos theta, and then we also multiply by the d theta, which is equal to du over cos theta. And then by some convenience, these two cos thetas cancel each other out, and we are then left to find the antiderivative of u, which is equal to 1 over 3 u raised to 3 plus u plus a constant. And that would be the answer to our first example. Now let's move on to our second example, which is the integral from 1 to 0, where we have in brackets 1 plus x raised to 3 halves, and the brackets is raised to 3 multiplied by x raised by half dx. And for this we have to define two parts again, which is u and du, where we can define u as 1 plus x raised to 3 halves, and the derivative of u with respect to x is equal to 3 over 2 x raised to half. And now we can find dx by making it the subject of the formula, which is equal to 2 over 3 du divided by x raised to a half. Now that we have dx again and u, we can substitute it into our original equation again. But before you do that, it is important to change these positions to u positions. And to do that, you just substitute these original values into your u function, and then you find your new u position. So we can say u equals to 1 plus 1, and then it's equal to 2, and u is equal to 1 plus 0, which is equal to 1. And then we have our new positions for our integral. So our new integral is from 1 to 2, where we have u raised to 3 multiplied by x raised to a half, and then we multiply the dx, where dx is 2 over 3 multiplied by du over x raised to a half. And then again, by some convenience, our x raised to a half cancels each other out. And we are left with the integral from 1 to 2, u raised to 3. We can take the constants out and multiply it by du. And finally, we can now perform normal integral operations on this equation, which then simplifies to 1 over 6 in brackets 2 raised by 4 minus 1 raised by 4, which is then equal to 5 over 2. And there we have our answer for example 2. Let's move on to our third example, which is the integral of a fraction where we have 2x minus 9 over a root of x squared minus 9x plus 1 multiplied by dx. Then we can define u as x squared minus 9x plus 1, and the derivative of u with respect to x is equal to 2x minus 9. And when we make dx the subject of the formula, then we have dx to be equal to du over 2x minus 9. And now that we have dx and u, we can substitute it into our equation and see what we get, which will be the integral of 2x minus 9 over the root of u multiplied by dx, which is du over 2x minus 9. And we are left with the integral of u raised to negative half multiplied by du, which is then equal to root u over 2. And that is our last answer for example 3.